Okay, so welcome everyone to the second day of the online open probability school. Thank you all for coming. It's a pleasure to have our second lecture from Jean-Christophe Mourrat on disordered systems and Hamilton-Jacobi equations. Just before we get to that, I'll remind you that the lectures are being recorded and posted on YouTube and on the course homepage, as well as being live streamed both on Zoom and on YouTube. So if you don't wish to be recorded, it's best to turn your video off and refrain from using the chat. That said, we welcome discussion in the chat and particular questions for the speaker, which either he'll respond to directly or the moderators will keep an eye on and flag to his attention if we see something important being raised. As with yesterday's lecture, we will probably have about half an hour followed by a short break, a small question period, and then the second half of the lecture followed by breakout rooms for participants. We ran, as promised, a couple of breakout rooms before the lecture as well. And I'd welcome any feedback from participants about how that went. I didn't pop into any of the rooms myself, so I'm not sure. Okay, so having said that, let me also remind you that there's a Zulip server for which you can create an account if you haven't already, designed for discussion about the various OOPS courses. The link is on the OOPS homepage. And that is a good resource for posting discussions that you maybe want to have less transients than the Zoom chat, which is not saved as part of the stream and disappears forever at the end of each lecture. All right, so once again, it's a pleasure to have Jean-Christophe Mourrat for his second of 3 lectures, and over to you, JC.
Thank you very much. So yeah, I'm very happy to be back here and to see that there are still many people joining. So I hope, so I thank again the organizers for making this possible. It's a real pleasure. And I'll try to start sharing my screen. Yes, it seems to be working. All right, so yesterday what we have done is, so first I tried to introduce the motivations behind what I want to discuss, and speaking a bit about this spin glass model, but only briefly, and also like waving my hands around this rank 1 estimation problem that I want to discuss later. And then I started to discuss or make some calculations about the Curie-Weiss model. And what we've done is see that there is, so if we look at this function I call the capital F sub n, it solves an approximate, it solves an equation which has some part that has a 1 over n in front. And so we were wondering, or it feels kind of plausible that in the limit, the limit object will solve the equation where instead of this 1 over n times second derivative, there is a 0. And then, so we have to pause a little bit and think carefully about what it means to solve this equation. So let me rewrite this here. So we need to think about what it means to be a solution of this equation, which is the one that we found for Curie-Weiss, except instead of 0, there was this 1 over n times second derivative with respect to this h parameter. And remember that in the setting of Curie-Weiss, this derivative with respect to h, we can interpret it as the mean magnetization of our system under our Gibbs measure. All right, so the first attempt I described at the very end of the lecture yesterday is what about we just ask for our function to be a C1 function and that it solves the equation pointwise. What I try to argue is that this is not going to be a good notion for us because if we kind of use our previous intuition about Ising models in general, we expect that there will be phase transitions for the magnetization. And so we expect that there will be jumps in the derivative. So although our functions are all Lipschitz with the same constant, it's not plausible that they will be C1 functions. So the derivatives will have jumps. So we need to lower our expectations about what being a solution to this equation should mean. And so I said again that our functions are Lipschitz. You remember that when we computed the derivatives, I pointed out that they are all bounded by 1. And so there's this theorem of Rademacher, which says that any function that is Lipschitz is differentiable almost everywhere. Okay, so we could say, what about we ask that the equation that is on display here is satisfied for almost every point? Okay, that sounds like something we can ask, and it sounds a second, perhaps more reasonable guess than our first guess. So let me write this. So what about we ask that f be Lipschitz? So I will not write it, but bear in mind that this means, in particular, that f is differentiable almost everywhere, and then we can ask whether or not the equation is satisfied almost everywhere. Okay? And solves the equation almost everywhere. And now the problem is that we are facing the opposite effect as our first attempt, which is, so initially with our attempt with C1 functions, we discovered that there is no existence, there will be, the function we actually want to see is not C1. And now it's kind of the opposite problem, which is that this condition I wrote down will not provide us with a uniqueness criterion. There will be many solutions for a given equation. So let me illustrate this. So let's say this is the problem. No uniqueness. So to really clarify this, let me start by forgetting about initial conditions and observing that there are some simple functions we can write down that are solutions. So for instance, 0 is a solution. Okay, that's pretty clear. Also, the mapping which to th associates t plus h is also a solution because the t derivative is 1 and the h derivative is 1. So when you do this computation with the partial t f minus partial f partial h squared, that will be 1 minus 1 squared, so it's also 0. And also if I look at t minus h, that's also a solution, right? Because the derivative in h will be minus 1, but still the equation will be satisfied. And the claim I'm going to make now is that from these 3 solutions, I can already make like new solutions that are going to contradict the uniqueness statement. So consider the following. So again, I'm going to draw a graph for a fixed t. And this is the h variable, and then what I draw is the value of the function. And so I'm going to do it like this. Okay, so it should be symmetric. It's like a 10 function. And the value here is h equals t. The value of the function on the top, like at h equals 0, is t. And this is t as well. So you see what I've done is that on this part, it's the function t minus h. On this part is t plus h. And outside of this 10th part, it's the zero function. So away from the corners, this is actually one of these three solutions I wrote down. And yes, so James, you're right. But then you see now I'm combining them, and okay, let me close this, and then I'll answer the question. So I hope you're convinced that this function, as I drew it, is a solution almost everywhere, because it's just at these corners that there are difficulties, but we're allowed to throw away a set of zero Lebesgue measure in these TH coordinates. So it's a solution, and you see that at t equals 0, it starts from the zero initial condition. But 0 is also a solution. Okay, so from the zero initial condition, we have the zero solution, and we also have this 10th function with this triangle that goes like this. Okay, and you can, in fact, decide to make this triangle appear at any time, and you can, in fact, make it be anywhere in space. So you have an infinite number of solutions like this. So to answer Jen's question in the chat, he was asking if the solutions that I wrote down here are not C1 solutions. So indeed, there are C1 solutions, but at least these ones, they don't have the same initial condition. So when I speak about uniqueness, I mean, given a value fixed at t equals 0, will this propagate into a unique solution, or will there be many? And a good counterexample is the one I drew, because this one starts from 0 and it's not the zero function. Okay, is this clear? Are there further questions? So we need to, like, it's a bit frustrating. We have to find some equilibrium between these two situations. But one thing that we can notice is that we can be pretty sure that the function I drew here is not the function we care about. And the reason is that we know that the function we care about, you remember, its second derivative is the variance of the magnetization. So in particular, it's non-negative. So in other words, we know that the function is convex in the h variable. And here we really have a breakdown of the convexity, okay? Not convex. And now the hope is that maybe if we add this further requirement of convexity, then this will finally select for us a unique solution. And I'm going to argue that this is the case. So it's not obvious a priori, but I'm going to discuss with you that this is true. So this is my proposal for the definition of the notion of solution. Let me write it. So we say, we say that a Lipschitz function f, so it's from R plus cross R and then valued in R, is a weak solution. Let's call it like this, okay, weak solution. Of the equation, I'll call it Hj, okay? So Hj is the equation we are going to focus on. It's the one that is here. The one which. So we're going to say this if the following two conditions happen. So first of all, that relation Hj is satisfied almost everywhere. And second, we have this convexity in H. Okay, so for every t, the mapping H gives f of th is convex. Okay, so now it rules out at least the counterexample I gave. But what I'm going to argue next is that indeed this selects a unique solution for us. So proposition. Yes, we can call it uniqueness. Let's phrase it like this. So if f and g are two weak solutions of the equation hj with the same initial condition. So the initial condition, I'll write it like this: 0 dot equals g of 0 dot. Then they are equal. Yes, so Peter is asking what's the intuition behind asking for convexity, and we'll see it in a moment when we do the proof. So I'm going to prove this proposition because I think it's really, in some sense, it's the powerhouse of the whole argument. So first, before I go into the proof, I want to take a step back and explain why I really want to insist on this proposition. Because maybe you think, why do we bother with this? This is a PD question. It doesn't talk about my probabilistic model. I want to that we come back to our probabilistic model. You know, in the before we pass to the limit anyway, everything is finite, everything is smooth. So why should we worry about this? But the point is that ultimately we want to understand the limit, and what we want to do really is a perturbation of the statement that is written. So what is written is that if we have two solutions with the same initial condition, then they are equal. But what we really want to have is, you know, when n is very large, we have something which is almost a solution, and we want to compare it with the true solution, and we want to say that they are close. Okay, so you see that it's going to be just a refinement of the statement that is written. Instead of two solutions must be equal, we are going to say one which is almost solution and one a solution, they are close. Okay, so really this is in some sense a simplification of the problem we're trying to do. Yes, so yes, so yeah, good questions. So Shuo is asking, what do I mean by this? Do I mean almost everywhere? So in fact here the functions are Lipschitz. So each time we speak about the functions themselves, it's really, we should really think of it as if you want a uniform type of, or at least locally uniform type of information. So here I mean really everywhere, in fact. You know, if you have it almost everywhere, by continuity, you can have it everywhere. So each time there are, you know, as a rule of thumb, let's say, each time we write identities involving derivatives, we will interpret them as almost everywhere. And each time we write identities involving functions, we will interpret that is actually everywhere. Okay. All right, so I hope you're on board with me that this is a useful statement to worry about. We should find a proof of that thing. So I'm going to give a slightly incomplete proof. So I'm going to call it a sketch of proof. And I will suggest that you think about how to make it fully rigorous. So let's study the I want to study the difference between these two functions, and I want to show that this difference is 0. So you know, I don't have much to do, so I have an equation for f and g, so I'm going to try to write an equation for the difference between f and g and see what it looks like. So if I differentiate in t the difference, essentially by definition, it's this derivative squared of f minus the derivative of g squared. And I'm going to try to make the difference appear again. So I can simply write this as this sum and then the derivative of the difference. Okay, so if I give a name to this, let's call it B. This is like by definition I call it B. Then what I just displayed is that dtw minus b dhw is equal to 0. Okay, and so in other words, when we look at the difference between two solutions, we can always think of it as, the difference is solving some sort of transport equation, the equation that I wrote here. So it's almost everywhere. Again, I don't write it each time. And now perhaps to start to answer a little bit the question of Peter in the chat, like why do we require convexity? Here, what will be of help really is that this B has its derivative has a sign. You see, the derivative of B itself, it involves the second derivative of H and the second derivative of G. So the derivative of B is positive. And in general, if you were doing a higher dimensional version of this argument, you would find that the divergence of this vector field, so there would be a vector field in place of B, and you would find that the divergence of this vector field has a sign. And the fact it has a sign, it means something about the lines of the vector field being either convergent or divergent. Anyway, this is what will allow us to figure out how to prove uniqueness. All right, so that was still kind of sketchy, but well, very sketchy. So let me start with a rough idea, and then I'll try to give a more precise, but still with this tiny gap argument. Okay, so the rough idea is that we're going to look at the integral of W in H, and look at how this evolves as a, yeah, maybe I could, yeah, okay, let me do this calculation and see if you find it convincing. So right now you may worry that this integral is not well defined because it's infinite, etc. But I just want to give the idea, so I kind of pretend everything is well defined in this step. Okay? So what happens if I differentiate in T this expression? Well, I will get the integral of the derivative of W. I won't write the variables again, but remember T is fixed and we're only integrating in the H variable. And we've said that this time derivative is B times the H derivative of W. And now if I integrate by parts, I can rewrite this as, and now I pretend there are no boundary terms, they are at infinity or something. What I get is this. And what we said is that this has a sign, it's non-negative. So if you imagine for a second that W starts to be positive, which means F starts to be above G, then naturally it will want to come back to being smaller, right? Because if W is positive, then this integral will want to be smaller again. And if W is negative, this integral will want to be positive, to go back to being close to 0 again. So there is this kind of effect of trying to come back to 0 in this relation. So there's a lot of things that are still very murky in my argument. For instance, I'm kind of pretending that W has a fixed sign, which is, there's no reason a priori to believe that. And also I integrate over the whole space, which is kind of probably not well defined either. So I'm going to now try to fix the argument, but I hope that this kind of very rough one-line chit chat gives you at least a taste of why having this convexity assumption will be of help for us. All right, so now this was perhaps what I write down in my draft. Now I'm going to try to do a real proof. So that's the closure of the rough idea. Okay, now I'm trying to do the real proof. So first I'm going to try to fix this aspect with the sign. I want to force a sign on W. And because, okay, you'll see that transport equations are nice for this. So let me define a function let's say x squared over 1 plus x squared. So, it's a nice, smooth function which has maximal slope equal to 1, and it's always non-negative, and it's 0 only at 0. Oh, yeah, W is the, yes. Yeah, okay, perfect. And I use this function to set V equals phi of W. Okay, so that's phi of F minus G. So now at least V is non-negative, okay? And our goal is to show that F is equal to G, so it's to show that W is equal to 0. But you see, it's equivalent to showing that this function V is equal to 0. So let me remind you what's the equation solved by W. It's here. Now what happens for V? Well, I claim that, in fact, that's the magic of transport equations. The same equation is satisfied for V as well. Okay, so if you think about it for a second, the time derivative of V is the time derivative of W times phi prime of W. And here it's the same. It's like the H derivative of W times phi prime of W. So this phi prime of W is kind of, you can factorize it. It's showing everywhere. And so it simplifies, and this relation is also valid. Okay, everyone is fine with that. So okay, I already kind of cleared out one aspect of my fake proof, which is that now V has a fixed sign. It's a non-negative. Now the second part I have to deal with is that I was integrating over the whole space. So I just have to, instead take an interval. And the problem with if I'm not paying attention is that when I do my integration by parse argument, it will produce boundary terms. And so I have to catch them back in some way. So the way I'm going to do this is that I'm going to, instead of integrating over a fixed interval, I'm going to change the size of the interval as I move along, so that it will produce me some extra good terms, if you want, that will allow me to catch back whatever shows up in the boundary terms in the integration by parts. Okay, so that was still perhaps a bit shaky, but so yeah, first one is asking why this function phi. It's really, I just want a function phi which is 0 only at 0, is non-negative, and has bounded derivative. So, I just picked that one, but whichever is fine. All right. So let me go forward and try to find this interval. So I introduced some notation before. So you remember the functions f and g are Lipschitz. So I'm going to, these are the Lipschitz constants in the variable h for f and g, and I just sum them up and I add one. And I will use this constant to fix the speed at which I change the size of my interval. And also, I keep making this movement with my hands. I hope you see it. So the size of the interval over which I integrate is going to shrink as time moves, and I'll just do a linear thing. Okay. So at some point it will just be a point, and then there will be nothing. So I have to fix a finite time, and then I start from there. So I fix a finite time. I'll call it capital T. And instead of this function that I had written capital I above, I propose that we study this thing. So J of T, the integral from minus L times capital T minus T to L times capital T minus T of V of TH dH. Okay, so it's I hope I try to, and oftentimes I just write it like this. So minus RT to RT. I'll just shorten this capital L times capital T minus T as RT. And then I just write V. Implicitly, I understand that there is a T and H. Okay. So T is fixed in the integral, and I only integrate over H. And then we let T vary and see what happens. Oh yeah, so first I should say this function J is Lipschitz in T. And so I can compute its derivative almost everywhere, and it is equal to the integral of this almost everywhere time derivative. And so let's minus RT to RT of dTV. So that's one part of the time derivative. Yes, and that's so yeah, ultimately I want to show that this function V is 0. Okay, so what I'm going to end up, I want to control the derivative of J. So what we're going to show is that the derivative of J is negative. So since it's a non-negative quantity, it starts from 0, it will be gone. All right, so the time derivative of this integral is, okay, one part is just differentiating under the integral, but there's also a part related to the fact that the boundaries of the interval are moving. Okay, so there will be minus L times V of T RT plus V of T minus RT. Okay, so they both appear with the minus sign in front because the interval is shrinking as time moves. Okay, so I produced these terms so that they would help me. I want to show that J does not increase, and so I'm very happy if I have that the time derivative of J is something with minus some positive terms. Okay, so these are just good for me. Okay. All right, and now I'm going to try to do my integration by parts thing in this term. Okay, so let's do this. So you remember the time derivative is B times this H derivative. And now I do my integration by parts. So it's minus integral from minus RT, oops, to RT of DHB times V. And I have these boundary terms. So maybe I'll write like this, B times V bracketed between minus RT and RT. Okay, and these are kind of more annoying for me. Like there will be at least one term which is not of the right sign. Yeah, so I'm not paying attention to passing integrals below the derivatives below the integral. So yeah, sorry about that. It's not a fully rigorous proof, but I think it's okay. You can just fail it. Yeah, but so this part you don't know a priori. At least there is one of these two terms which does not have the right sign for you. It may have the tendency to let J increase. The one with which comes with a plus. There will be plus B, this BV evaluated at T, RT. But the point is that, at least my hope, is that it can be compensated by these minus terms that we had here. And do you see why this is true? Is that, okay, so we have V of T and RT, which is also here. And now the claim is that B is bounded is smaller than this coefficient L. So I chose this L so that this happens. So let's verify that I did not mess it up. So remember the definition of B is a bit further above. It's here. It's the sum of these derivatives. And the way I chose L is an upper bound on these things. I summed the L infinity norm of these guys. Okay, so long story short, if I take this minus this guy, it's a negative quantity. I say negative in the sense of maybe it's 0 or it's in a wide, I mean less than or equal to 0. Okay, so in other words, these boundary terms don't bother us, and what we have is just this. Okay, and now finally, as promised, this is non-negative, and this also is non-negative. Or maybe I should say just positive. I never know if I should say positive or non-negative. Anyway, it's greater than or equal to 0, and so the whole thing is less than or equal to 0, and that's it. That's what I wanted to show. So dtj is less than or equal to 0. And why do I say that's all what I wanted to show is that j at 0 is 0. And j is non-negative, right? Because it's the integral of this v function, and v is non-negative. So what we have shown is that we conclude that j is constantly equal to 0. Okay, so that means that v is equal to 0, and perhaps initially you can only conclude that it's true almost everywhere because we have this integral. We integrated against the Lebesgue measure, but it's a Lipschitz function. So as we discussed before, by continuity you can complete, and you just conclude that v is equal to 0, and this means f is equal to g. Okay, and that's the end of the argument. I drew a triangle because some parts were not completely rigorous. So yeah, Fardal was pointing out that I was not really paying attention to interchange of derivative and integral. That's true. And also another aspect which I was kind of careless about is that if you look at B, it's not really differentiable. So I was using this, I'm sorry, I want to display the definition of B again. It's here. Let me square it. You see, in the argument, I use this derivative of B with respect to H. And it's not clear a priori that it makes sense because I only know that F and G are Lipschitz. So in particular, they are not twice differentiable. So my proposal as an exercise, and I think some of you are taking this for credits also. So the exercise is to make this proof rigorous. And yeah, so let's say this is part of the credit assignment for those who take credits. And if you, so the idea, I think, if you really want to make it rigorous, is to convolve a little bit B by a smooth kernel. And if you struggle, you can have a look in the book of Evans on PDs. It is done there as well. So I think it's already almost late for a break. So anyway, let's take a break now, and I'll be happy to take questions maybe before we turn to that. So are there questions on this?
Question on the chat.
Yes. So Andrew is asking if this is equivalent to the notion of viscosity solution. So in the case when the initial condition is convex and Lipschitz, then the answer is yes. But so what really makes this proof work? So you can weaken the proof in several ways. Sorry. You don't really need to assume that it's that the function is convex in H. It would suffice that it's semi-convex. That you just have lower bound on the Hessian. Maybe it's negative, but that would suffice. And yeah, so maybe I just I should not have scored that. It's too long now. So in general, you can try to see what happens with more, even in higher dimension. Like if you try to make sense of equations of this form, and the thing that really makes the proof work here is that this nonlinearity is convex. So if you think carefully about how we argue in the argument in the proof, this is really what is necessary for the things to work out nicely. So really the power of the notion of viscosity solution comes mostly when this nonlinearity is not convex, or I should say neither convex nor concave. But whenever the nonlinearity is convex or concave, the two notions will coincide. So Parton is asking, what does it mean from the physics point of view? I mean, for starters, it's not perhaps completely easy what it means, this function fn. Okay, or maybe you can. Yeah, so this function fn, okay, it's a free energy. And yeah, the fact that it's convex in this h parameter is a very robust feature of the models. Each time you construct this free energy like this with the parameter times some quantity, when you differentiate twice, the second derivative will be a variance. So you will always have this convexity property. So I'm not sure exactly how to phrase it best in terms of the physics, but I guess you could say that it's the convex conjugate of some other reasonable function of physics, which, okay, what should it be? Yeah, okay, I'm not sure. I think one could do a reasonable argument, but yeah, so Pierre Francesco is saying Legendre transform, but I guess the question is, it's the Legendre transform of what, right? And maybe it's the Legendre transform. Yeah. Okay, maybe it's the Legendre transform of the large deviation function or something.
Okay, so maybe that's a good moment for just a 2-minute breather, and we'll resume very shortly. Does that sound okay, Jean-Christophe?
Yeah, absolutely.
Great. Maybe it's 12:45, so it's a good time to pick up again anyway. If everyone
okay, sorry.
if everyone has the energy.
Yeah, so I don't know what, like for me, a Legendre transform means when you do this like functional Legendre transform, and by definition, it gives a convex function. So in my opinion, if it's a Legendre transform, it means it's going to be convex. But okay. And yeah, so then I'm not super. I'm too much of a mathematician to be sure about what free energy means when I don't write a formula. So yeah, so it's possible that in some cases it makes sense to speak about the free energy which is not convex. But I'm not going to dwell too much on this because I'm not sure if I would. I think I would probably say stupid things. All right, so I have perhaps one more comment. I won't insist very much on the existence aspects for these equations because in some sense, for us, this comes for free. We're studying a model and we are wondering if it converges to something. So the only thing we need to worry about is to show that this thing is converging. So the fact that it will, that we will produce some solution is almost given because any limit point basically should be a solution if we are not giving a bad definition of solution. So perhaps another way to say it is that you could try to run the proof that I just gave you. Just instead of speaking about solutions, you would use it to try to show that the sequence of functions fn is a Cauchy sequence. Okay, and you would manage to do that argument. So you would not know existence of solutions, but you would show that this is a Cauchy sequence, and so therefore it converges, and then the limit you would show it's a solution. So yes, but in case you're I think it's still, despite the fact that I think it's not critical to worry about existence aspects, I think it's useful to have in mind that we can write down a formula for the solution. So I'm not going to dwell on this too much, partly because time is running short. But so in the settings that we are exploring, the function so if I take the supremum of psi of h minus h prime minus h prime squared over 4t, then I claim that this is the weak solution. And I say the because we've shown it's unique. So here I'm assuming let's just say that psi is convex and Lipschitz. And then, so the claim is that if you write down this variational formula here for f, then it's actually the solution of the equation. Okay, so in general, what appears here is related to the convex dual of the nonlinearity of the equation. So in our case, the nonlinearity was just the square function. Maybe I should write with a different color. Maybe I write p gives p squared. And the convex dual of this function is, let's say, q gives q squared over 4. And so you see that there is some q squared over 4 showing up in there. So in general, this expression is related to the convex dual. So I'm not going to prove this, but again, the fact that a formula like this, one can write a formula like this is related to the fact that the nonlinearity in the equation is convex. So yeah, I'm not going to prove this, but see Evans if you want to see a justification. And yeah, so let me propose another exercise. So not necessarily for credit, but just for your, I think it's a useful exercise. So in the setting that we have a specific definition for psi. But okay, what I really want to use about psi in this exercise is just that it's a smooth function. It has 0 derivative and it has a positive second derivative at 0. So show that for t small, you have still a 0 derivative for the solution at 0. You can use the Hopflax formula for doing this exercise. And for t finite but large, on the other hand, you have that the derivative on the positive side is positive, and okay, it's kind of implied that the derivative on the other side will be negative. Okay, so for using the Hopflax formula, for instance, you can show that there is a phase transition in this derivative. Okay, so maybe I call this the third part. So I hope I'll try to, my goal is to wrap up the study of the Curie-Weiss model from what we have now. And perhaps before so what I really want to show ultimately is that this sequence of functions fn converges to f. I think this by now has become clear. But I've often emphasized that the physics, the information that we perhaps most care about is this mean magnetization, which is encoded in the derivative of the function. And it's not clear a priori that by knowing the convergence of the function, we understand something about the derivatives. Oh yes, there are f's missing in the, thanks for the, there are f's here. Thank you very much. Yes, I think you can compute the, but then, so Fusuan is asking if we can identify the precise t at which the transition happens, but this requires a more subtle analysis, but this is possible, yes. I mean, you have to, this exercise is more, showing the exercise is easier than showing what you ask, but it's also possible to do what you say. All right, so yes, I want to first explain that indeed we understand, if we understand the convergence of the functions, actually we do understand the convergence of the derivatives as well, which is perhaps not obvious a priori. So let me state this. So if TH is a point of differentiability, differentiability in H of F. Okay, so maybe this is not. So by this I mean at the point TH, the function F is differentiable, and if you want to be precise, differentiability only as H varies would be sufficient. Okay, and if Fn converges to F, then actually the derivatives at this point TH converge to the limit derivative. Then dH Fn at TH converges to dH F at TH. So really, if we understand something about the derivatives of the limit, actually we do understand something about the derivatives before passing to the limit. All right, so let me try to prove that statement. So now I'm back into the setting of the Curie-Weiss model, right? Fn is the function that was defined in this setting. And the engine of, the reason why the statement is true is that the function is convex in H. Okay, so if I look at Fn of T prime H prime, this will always be above the tangent at the point TH. Oh, no, I just mean, sorry, I just mean to move H. I'll just fix T. So, okay, so you always have this property because the function is convex. Yeah, the convergence is for this locally uniformly. Okay, so this is by assumption because the function is convex. And now assume that, so this is bounded. So take a subsequence along which this converges. And let me call the limit along this subsequence P. Okay, so then what happens when I let n tend to infinity? So as was asked in the chat, the convergence is pointwise. So yeah, so pointwise or uniformly would be the same. So let's say pointwise. Sorry, as I pass to the limit, then it becomes f of th prime is always above f of th plus this slope p times h prime minus h. And so I found an affine function which touches f at the point th and which is always below the function f. And if the point is a point of differentiability, there's no other way than for p to be the derivative of f. Okay, so p must be dhf at th. Okay, and that completes the proof. Okay, this one is actually fully rigorous. It's so really, yeah, we do understand what happens for the true problem, even at the level of the derivatives, if we understand the convergence of the function. All right, and yeah, in the short time that I have left, I want to complete the convergence of this function fn. Okay, so now I hope someone named K asks why such a subsequence can be found. The derivatives are bounded. Okay, remember that the function is Lipschitz, so I can always extract a subsequence. Yes, so I hope I convince you that the convergence of Fn should be like some sort of more refined or like a perturbation of the uniqueness argument. Okay, so because now we're dealing with a function which is almost a solution, and we're going to say it's close to the true solution. So let me recall you the equation. So dt Fn minus dh Fn squared equals 1 over n dh2 Fn. Okay, so now it's not exactly a solution. There's this extra right-hand side, and I want to still say that it's close to the true solution. I'll still call little f the true solution. And so really I'm trying to mimic the same argument. I'm defining the difference. And when I define the difference, it solves an equation like before. So it will be a b times dhw. So I don't write sub n, but it depends on n, also w and b. And then on the right-hand side, I have this extra second derivative. So where b is, as before, is the sum of the derivatives of the function. So dhfn plus dhf. Okay, and now what else did I do before? Yes, I took then, I applied this function phi to make the difference have a sign. Okay, so now then I set v equals phi of w. And before it was really nice, it solved the same equation, but now I have to be a little bit more careful. So I have dtv minus b dhv equals, and now, okay, I have this phi prime w, which is still kind of around. So it's phi prime of w times 1 over n dh2 fn. Okay. So you see, again, it's really very close. Yeah, same phi, x squared over 1 plus x squared. So it's really very close. The argument is really very similar to what we've done before, except that there is this, this bit of right-hand side that we want to see is small. And so we define again this j of t, which is integral from minus rt to rt of v of th dh. And rt is defined as before. There is this constant L inside, but L is the sum of these L infinity norms of Fn. And so you can, we know that these h derivatives are all bounded by 1. So if you want, you can, the way I define L was the sum of 3 terms. So you can just take L equal to 3 in this proof. Okay, and that's what L is. And we run the argument again. And so before we found this, but here the novelty is that there is this extra term which comes from this junk on the right-hand side. So I'll just write it. So phi prime of w times 1 over n dh2 fn. Okay, and so it's of th dh. Yeah, I should have written w of th also. And now we have to deal with this term. And the nice thing is that, so phi prime is bounded by 1. And this is non-negative. Okay, fn is convex. So I'm using this again here to deduce that the time derivative of j is bounded by integral from minus rt to rt of, okay, maybe I put 1 over n outside, of the second derivative of fn, th dh. And you see, I don't put absolute values because I know it has a sign. And it's very convenient for me because then it's the integral of the derivative. So this is 1 over n times the derivative only one time, the first derivative of fn between the two bounds, minus RT to RT. And now we've said several times that this h derivative is bounded by 1. So this whole quantity is bounded by 2 over n. Okay, so what we have proved here is that the time derivative of j is bounded by 2 over n. And recall that the initial condition is they coincide, right? The initial condition of fn is constant and is the same as that for a little left. So j of 0 is equal to 0. And its time derivative is bounded by 2 over n. So what we have shown is that j of t is bounded by 2t over n. Okay, and then I kind of close this here because I'm kind of running out of time a little bit, but you see that this should kind of close the argument, at least in this L1 in age and L infinity in time, we have a good control on the difference between Fn and F. And now if you want to have really pointwise control on the difference between Fn and F, you can upgrade because you know that all the functions are Lipschitz. So if I tell you that two functions are close in L1 and they are both Lipschitz functions, then you can deduce they are close in L infinity. If you maybe you lose a bit in terms of the rate, but you can still do that. So maybe I'll add as an exercise, again, not necessarily for credit, but just clean up this. Okay, so there were a few things that were not very rigorous. So again, I was kind of, yeah. Okay, so that's, I think the thing that is most important to clean up is how do you get pointwise convergence from this kind of L1 convergence. But in any case, so now, okay, we can breathe. That's the end of the argument, and I really want that we bring with us for the last lecture an important message, which is the following. So key point. So when we are going to face the problem in the rank 1 matrix, again, we will find some quantity similar to Fn. Sorry, there's a question in the chat about where does this bound 2 over n comes from. So this is the difference of two, the evaluation of the derivative at 2 points, and each of these guys is bounded is between -1 and 1. So I just sum them up and it gives me a 2. Okay, and you remember this h derivative is the mean magnetization, so it's between -1 and 1. Yes, so in the future we will have a very similar situation with a function which almost satisfies the same equation, in fact. And we are going to try to show it converges to the true solution. And the key point to remember is that what we need to, if I write an equation for Fn or some variant with some, let's call it some errors on the right-hand side, ultimately what I have to do in this argument is to understand some L1 estimate, some integral over h of this quantity. Okay, so the key point I want us to remember is that, so let me write like that. So if there are error terms on the right-hand side, I hope you see what I mean by this, like whatever shows up on the right-hand side of the equation that we kind of don't like and hope goes to 0. We need to estimate it in L1 in the h variable. And uniformly in H. And all this I mean locally. Okay, so locally in L1 and locally uniformly in H. So if you want a short summary of that statement, is that I want a local L infinity in time, L1 in H estimate. Okay, so the claim I'm making here, which you can play with this if you want, is that you can write down a marginal version of that statement we just went through, in which there is something that solves an equation with some right-hand side. And if the right-hand side is small in this sense, like locally L infinity in time, L1 in H, then the argument will work and we will manage to show closeness with the real solution. Okay, so that's the main thing I want us to remember for next time. And I'll stop here. I think it's a good time for questions.
Okay, great. And just before we go to questions, I think I don't know how the rest of you felt or how all of you felt, but as the organizer, I think it's very nice to unmute everyone and give a round of applause before we go to questions. So thanks again for a lovely lecture, Jean-Christophe.